Hello everyone, welcome to CCNA Scaling Networks version 6, chapter 5, Dynamic Routing. So let's have a look at dynamic routing protocols and how they're put together. So we've got two major classes. We've got interior and exterior. And inside the interior we've got distance vector and link state. RIP and RIP version 2 were pretty early on. Cisco's liked everything that was in RIP and they made EIGRP, but then OSPF is quite a different routing protocol. So we're going to go through and we're going to have a look at the different types of routing protocols. Almost all the routing protocols we need to cover have both an IPv4 and an IPv6 version. So let's go through and see what we've got. Most routing protocols need to maintain some sort of tables. So EIGRP has got a neighbor table, which is a table of all of their immediately connected neighbors. They've got a topology table, which is where all the routes are, where they should go. And they've got a forwarding table, which is what they give to the router to say, hey, look, I reckon this is the best way to get there. They have lots of different types of traffic. They've got hello packets and updates and query packets, and those sort of packets need to be acknowledged. So, and also there's replies. So if you send a query, hey, how do I get to this place? Then EIGRP has a reply and it's going to reply to that. EIGRP uses the dual algorithm, and OSPF, which we're going to look at shortly, uses the open shortest path, or shortest path first algorithm. But it's important to note that they need tables. Once again, a routing table, the larger the route table, the more unhappy your router is going to be. So you need your route tables to be as small as possible. Why do we even need static routing? Why do we even need dynamic routing? Let's have a look at some pros and cons. Static routing, very easy to set up in a small network. But once your network gets bigger, they become a bit more unmanageable. They're super secure because they're static. There's nothing dynamic about them. They can't be learned or injected or manipulated in any way. However, when things change, when links go up, links go down, you need to be able to recover, to respond to that dynamically. So therefore, that's why dynamic routing is much more appeasing in a medium to large network. There are still places for static routes, but mostly dynamic routing protocol is what you want. However, bear in mind, the bigger your network, the more dynamic routing protocols, the more CPU and RAM you're going to need. So make sure you scope and scale your routers with enough CPU and RAM. Bit of a keeping on with the history lesson. We've got our two broad categories of interior and exterior. And then inside interior, we've got distance vector and link state. These two very broad classifications are very straightforward. Distance vectors have got two key characteristics. The first one is they can only know what to do based on what their neighbor has told them. They learn by their neighbors. The neighbors tell them what to do. Link state, on the other hand, is the complete opposite. Every router must know every link to every destination in the whole network. Every router has a whole overview of the entire topology. Distance vector can only know what his neighbor has to tell it. So RIP and IGRP came out pretty much the same time, and then RIP version 2 came out, and then OSPF was on the market, and Cisco realized that IGRP had some limitations, so they made enhanced interior gateway routing protocol. Even though IGRP is listed there, and if you do a question mark in the router, you'll see it, most iOSs now don't even have it installed because it's so old and not used at all. If you're thinking you might want to use IGRP, you should basically use either EIGRP or OSPF anyway. And exterior, we've got BGP. BGP is pretty much the only one now that survived, and that's all about path. That's all about the way the internet is connected together. Let's have a look more of that in more detail. So we've got 3 companies and 2 ISPs. So inside company number 1, we've got EIGRP running internally. Inside company 2, we've got OSPF running internally. And inside company 3, we've got RIP running internally. We've got 2 ISPs, and they are both running BGP between the connections. he's got OSPF, he's got ISS. Now, this guy over here, company number 3, he doesn't need a dynamic routing protocol between him and the ISP, because there's no choice, there's no variation, there's nothing dynamically that needs to be learned or taught on this link at all. Just static route, easy. But this guy's got 2 ISPs, this guy's got 2 ISPs, and the ISPs talk to each other. So they need a dynamic routing protocol to learn about why the network is put together. So interior, inside the networks, exterior, between companies, between. So bit of a broad chart, but we'll work our way through it. So we've got RIP version 1, version 2, 30 seconds, periodic, small networks. RIP version 2 can support VLSM, RIP version 2 does not. Their administrative distance, in other words the trustworthiness of the routing protocol itself, is 120, and the metric they use is hop count. IGRP is also slow, but look at that, 90 seconds, even slower than RIP, that it uses bandwidth and delay. But then Cisco realized and they enhanced IGRP. They made it faster. They made it be able to scale to bigger networks. They made it to be able to support wacky subnets. But it needs a bit of CPU and RAM, and you need to know a bit of knowledge about it. And it uses bandwidth and delay for the metric. And OSPF, very fast. In fact, the fastest of them all. But look at the complexity, very high complexity. And it only cares about cost. Now, notice how the routes information share. So RIP version 1 and IGRP are broadcast, and all the others talk to each other via multicasts. Just a little dodgy thing about Cisco's RIP implementation. All distance vector routing protocols are meant to be periodic. So every 30 seconds, they do what they got to do. But Cisco have actually added in a little tweak in their version of RIP. So there's a little event driven as well. So when an interface goes down or a new network is added, it resets the 30-second timer back to 0 and then starts again. But if you've got an environment where you've got Cisco, HP, Nortel, Juniper, all running RIP version 1 or 2, you're going to notice that 30 seconds, 29 seconds for things to update and everyone to learn whatever's going on. All right, let's have a bit of a breakdown of the routing protocol and how it's put together. So we've got 3 routers, the left, the middle, and the right, and they're all plugged in. So we turn on the first router, and immediately we have one directly connected network, the fast Ethernet 0/0. And because we're using RIP, the red circle represents hop count. It's 0 hops. It's directly connected to that router. We turn on the middle router, and the serial link comes up. So now router 1 has got 2 connections, and router 2's got 2 connections. Network 1 and 2 on router 1, and network 2 and 3 on router 2. But RIP, he's going to send a broadcast saying, hey, I've got these 2 networks, network 1 and network 2. But the middle router is going to look at that and say, you know what? I already have a better path to network 2, and that's directly connected, and that's got 0 hops, and you're trying to tell me that's got 1 hops. So this information, as far as I'm concerned, thanks for telling me, but it's no value. I'm gonna get that information and chuck it in the bin. And this router is going to send the entire route table, because that's what RIP does, the entire route table every 30 seconds, onto this guy. But look, he's got network 2 and network 1 already. So we don't need those anymore. So let's get rid of those, and we'll age them out because their metric is worse than what I currently already know. So the next thing we're going to do is we're going to turn on the third router. So now that serial link comes up, and then we've got connectivity between that router, the right hand router, and the center router, broadcasting there. He's going to send, the middle router sends the entire route table, all 4 entries. But as you can see, network 4 is no good because that's already 1 hop away, and he knows already about that. So we'll get rid of network 4. So now router 3 has got 5 entries in his route table. He's going to send the entire thing over to the center. Same process as before. He's going to receive those 5 entries, and he's going to age out the ones that are not important. So network 4 he knows a better way, network 3 he knows a better way, network 2 he knows a better way, network 1 he knows a better way. Remembering that RIP sends the entire route table every 30 seconds. So now the center router, what's he going to do? He's going to send the entire route table off to router number 1. And of course, let's throw away the networks that are worse. So what is the definition of a converged network? This is it. We've got 3 routers and there are 5 networks. All 5 networks are known by all 3 routers. So everywhere is known, all the paths are known. Periodic and triggered. Well, periodic happens on a periodic, like time. In RIP it's every 30 seconds. And for OSPF it's event driven, so it only sends updates when there's a change. Show IP protocols, very useful command. You'll be using it lots and lots. So let's have a look at this one. First thing that we can pull out about this, first thing is RIP. Second thing we can pull out is the timers. So sends update every 30 seconds, and just by the by, next one's due in 16 seconds. So we're going to send information every 30 seconds, but look at the hold time and the flushed after and the invalid. If we don't hear information about a network, we're going to still hold on to that information for a little while. So we're going to keep holding on for 180 seconds. And then after 180 seconds, we're going to say, no, this is gone. This network's not here anymore. And after 240 seconds, we're going to chuck it in the bin completely. RIP's got 2 versions, version 1 and version 2. Notice that it can send 1 and receive 1 and 2. But if you change it to 2, then it can only send 2 and it can only receive 2. If you're doing crazy wacky subnetting of VLSM or classless interdomain routing, summarization is something you need to consider. This is the list of networks that are being advertised, and this is where we're learning information. This is the only guy we can see at the moment, and he's telling us all we need to know. Remember that this is a distance vector routing protocol, and we can only learn from our neighbors. So see here how we have a routing process and then all the information goes in there like network statements. 6, we have a routing process command, but the actual commands live inside each interface. So we don't have any network statements in IPv6. So all we have to do is enable it. So we go IPv6 router RIP and we give it a name or a tag. And then you've enable that tag inside the interface. So I've just called it Josh RIP so that it stands out as being something a bit wacky. And always remember to turn on IPv6 unicast routing. So IPv4, network statements in the router process. IPv6, commands inside each interface that you want to be advertising with that protocol. So OSPF uses shortest path first algorithm. So I've got this lovely diamond here. So all the routers know all the path costs to everywhere. So just the example we've got here is that the top router, how to get to the Ethernet segment on router 3, it's cumulative. So we start here and we want to get to here to here. So this path is 20, 25, 27. This path would be 10, 20, 40, 5, 47. This path would be 20, 40, 52. Do you know what I mean? So it knows all the different path costs and it just does the math and it knows all the paths and says, right, well, 27. 27 is the actual lowest numbered way of getting there. So that's why it's called shortest path first. Link state protocols got some big advantages because they are very powerful and they know everything. They're super fast, and the link state information is sent only when there's a change. So there's no broadcast every 30 seconds or whatever. It's a hierarchical design, keeps a full database of everything. However, OSPF has a huge disadvantage, and that is that when it's got something to say, it can flood your whole network. So maintaining the database and sending out all the information that it needs to talk to its neighbors when there's a change, it can literally flood your whole network. So yes, calculating the shortest path first algorithm takes CPU and RAM, But when it's got something, when it's got work to do, it doesn't care about user data. It can literally flood your whole network. So the way we help OSPF to not flood the whole network when there's a change is we make areas. So we've got area 0, area 51, and area 1. So notice that there's a problem inside area 51. So all those 5 routers in there, they've got a lot of work to do. But only those 5 routers. The other routers don't need to know about that. They just say, oh, okay, whatever. You just when you're finished, you tell me what you need to do, and everything will be fine. So it decreases the amount of flooding that OSPF has to do. But if this is just one big area, as soon as there's a change in the network, every single router in the whole network needs to know about it. And that could cause disruptions to user data. OSPF cares about cost, and that cost is a representation of bandwidth. So in this scenario, we have the T3 links are fast, and we've got 2 T1 links that are slow. So OSPF recognizes the speed of the links and says, you know what? I'm going to choose the faster path. Yes, it's more routers to go through, but it's faster. Whereas if we just put RIP, even RIP version 2 in this network, it'll just look at hop count and say, you know what? Hop count is all I care about, so I'm just going to use the hop counts to get from A to B. And this is why you need to have a more dynamic routing protocol, because they're more, a link state routing protocol in this scenario, because it takes the optimal path rather than just the shortest path. So, a lot of words on this summary, sorry about this, but dynamic router protocols are awesome and they do things dynamically, which is great. However, they do need CPU and RAM. You pretty much always need at least one static route in your network to get off to the public internet or wherever, and the rest of the network's taken care of with dynamic routing table. Convergence is when all of our routers are happy and they know everything about the network. The administrative distance is the trustworthiness of the routing protocol, and a metric is the trustworthiness of the route itself. Distance vector routing protocols only know what their neighbors have to tell them, and they're periodic, every 30 seconds, etc. Whereas a link state has an entire overview of the whole topology that it worked really hard to get. And the link state routing protocols use the shortest path first algorithm, and it's all about the cost. It's the cumulative cost of the network. So that's how it does a loop-free best path option. All right, thanks for your time, and we'll see you in the next one.